This is Physics 2110, Lecture 12, and today we're going to start talking about magnetic fields and magnetic forces. So before we begin, let's kind of review a history of magnetism. We've known about magnetism for a long time. In fact, in 13th century BC, the Chinese first used a compass, used a magnetic needle. It was probably, they think, an invention of Arabic and Indian origin, but it was in use as early as the 13th century BC. And in 800 BC, the Greeks discovered magnetite, in that it attracted different pieces of iron. In 1269, Pierre de Méricourt found that the direction of a needle near a spherical natural magnet formed lines that encircled the sphere. And the lines passed through 2 points diametrically opposed to each other, and he called those points poles. In 1600, William Gilbert expanded experiments with magnetism to a variety of different materials, and he was the first to suggest that Earth itself was a large permanent magnet. And then in 1819, Hans Christian Ørsted discovered the relationship between electricity and magnetism. Essentially, he found that an electric current in a wire deflected a nearby compass needle. So this is the beginning of our look to see how electricity and magnetism were related to each other. And then in the 1820s, Faraday and Henry developed further connections between electricity and magnetism, essentially found that a changing magnetic field created an electric field. And then finally, Maxwell said a changing electric field produced a magnetic field. So magnetic fields and electric fields are closely related. In fact, we'll study Maxwell's 4 equations, which puts all of the relationships between electricity and magnetism together. So in considering magnets, the first thing we want to consider is magnetic poles. Every magnet, regardless of its shape, has 2 poles, and we call these a north and south pole. And they exert forces on one another, similar to the way electric charges exert forces on each other. Like poles repel each other. So 2 north poles will push each other apart, or 2 south poles. Whereas unlike poles attract each other. North and south poles pull each other together. Now, the poles received their names due to the way that the magnets behaved in the Earth's magnetic field. If I have a bar magnet and I suspend it so it can move around freely, it rotates. And the magnetic north pole points towards the Earth's north geographical pole. Now, that means that the Earth's north geographical pole is a magnetic south pole. And similarly, the Earth's south geographic pole is a magnetic north pole. The force between these 2 poles varies as the inverse of the square of the distance between them, similar to electricity. Now, in electricity, we can have a single isolated charge. However, magnetism, there is no such thing as a magnetic monopole. In other words, magnetic poles always are found in pairs. There is some theoretical basis for the existence of monopoles, a single pole, a northern magnetic charge. However, we have never seen one, even though we have looked at them for quite some time. So magnetic fields are going to be similar to electric fields. And we're going to symbolize a magnetic field by the variable B. Direction is given by the direction a north pole of a compass needle points at that location. And then we can use a compass then to trace out magnetic field lines and to see what these magnetic field lines look like. And if I were to take a compass around this magnet and move it around in different directions, the magnet's going to point and it's going to come out of the north pole and go into the south pole. We can also use iron filings because they're essentially little metal slivers, little iron slivers that act as little permanent magnets, and they line up along the magnetic field. And so we see the field lines coming out of one pole, going around into the other pole. And we can use iron filings then to look at the patterns of magnetic field lines for different combinations of northern and southern poles. So for example, if I take a north pole of one magnet and a south pole of another, I get a magnetic field pattern that looks like this. This is very similar to the electric field lines from an electric dipole. Or if I take iron filings to show the direction of the field of two northern magnets, this looks just like the electric field lines due to two like charges. So we need to define a magnetic field. The magnetic field at some point in space can be defined in terms of a force that it exerts on a particle. The magnetic force will be exerted on a charged particle moving with a velocity v. Now, when we are considering all this, let's ignore any gravitational effects, ignore any electrical effects, and just look at the magnetic field. So the magnetic field magnitude that is exerted on a particle is proportional to the charge of the particle to the speed of the particle. And the magnitude and direction of the force depend on the velocity of the particle and the magnitude of the direction of the magnetic field B. When a charged particle moves parallel to a magnetic field line, the magnetic force acting on it is 0. And when the particle's velocity vector makes an angle theta with the magnetic field, there's a force that acts on it, and it's in a direction that's perpendicular both to the velocity and to the magnetic field. Now, the force exerted on a positive charge is in the direction opposite of the magnetic force exerted on a negative charge that's moving in the same direction. And we also know that the magnetic field is proportional to the sine of theta, where theta is the angle between the particle's velocity and the direction of the magnetic field lines. So, we need to put this all together. We said F is perpendicular to both the field and the velocity. So if I were to create a plane that consists of the velocity vector and the magnetic field, we know that the force is perpendicular to both of those. And oppositely directed forces exerted on oppositely charged particles cause the particles to move in opposite directions. So a negative charge moving up in this magnetic field experiences a force in an opposite direction than a positive charge. So if we put all of these together, the vector equation for the magnetic force is the charge times the velocity vector crossed with the magnetic field vector. This is the cross product, the same cross product we introduced last semester when we talked about torques. Now, in order to figure out the direction of the force, we can use the right-hand rule. There's a couple of different ways to use the right-hand rule. The first one is to use your hand with your fingers coiled up and the thumb pointing up. So, we take our fingers and we point them in the direction of the velocity of the particles. And then we bring our fingers in to a direction that the magnetic field line's in. So we'll be having an open palm and closing it so that our fingers are now pointing in the direction of the magnetic field. And as we do that, our thumb is going to point in the direction of the force. An alternate to this rule is to use an open palm, where your thumb points in the direction of the velocity vector of the particle, your fingers point in the direction of the magnetic field, and your hand then is going to push in the direction of the magnetic force. Now, you can use either one of these rules, whichever one is more comfortable to you. The magnitude of the magnetic force on a charged particle is given by that cross product. Remember, cross product is the magnitude of one vector times the magnitude of the other vector times the sine of the angle between them. So the magnitude is QVB times the sine of the angle between them, where theta is always the smaller of the angles between V and B. So then, F is 0 when V and B are parallel or anti-parallel to each other, and it's at a maximum when V and B are perpendicular to each other. So what's the difference between electric and magnetic fields? The first is the direction of the force. The electric force acts along the direction of the electric field, whereas the magnetic field acts perpendicular to the magnetic field. Electric forces act on a charged particle whether it's moving or not. However, magnetic forces only act on charged particles when it is in motion. Magnetic forces cannot affect a stationary particle. And the electric force does work in displacing a charged particle. However, the magnetic force associated with a steady magnetic field does no work when a particle is displaced. It's because the force is always perpendicular to displacement. If we remember our equation for work that we do, it's the integral of force dot ds. But force is proportional to velocity, so perpendicular to velocity, so force is perpendicular to ds. So when we take the dot product of two vectors that are perpendicular, we get 0. So therefore, the work done on a particle by a magnetic field is always 0. What does that mean? It means that magnetic fields can change direction, but they can't change speed. They can't change the 1/2 mv squared. The kinetic energy of a charged particle moving through a magnetic field cannot be altered by the magnetic field alone. So when a charged particle moves with a velocity v through a magnetic field, the field alters the direction of the velocity, but not the speed or the kinetic energy. The units of magnetic field are the Tesla. A Tesla is a Weber per meter squared, or a Newton per Coulomb meter per second, or a Newton per amp meter. WB is a Weber, and it's a measure of flux. We'll get to that a little bit later. In CGS units, centimeter gram second units, the unit is a Gauss. And 1 Tesla is 10 to the 4th Gauss. Now if we look at some typical magnetic field values that we might experience, very super strong laboratory magnets may get up to 30 Tesla, or very strong laboratory magnets that aren't superconducting can get up to maybe 2 Tesla. An MRI unit at your hospital is a pretty strong magnetic field. It's 1.5 Tesla. A bar magnet is maybe 1/100th of a Tesla, and the magnetic field at the surface of the sun is about the same. On the surface of the Earth, it's about 0.5 times 10 to the minus 4 Tesla, or magnetic fields due to nerve impulses in your brain might be 10 to the minus 13th Tesla. So a lot of the magnetic fields that we're going to be dealing with are pretty small. That's why a lot of times when you see a magnetic field, it'll be measured in Gauss, not in Tesla. That's just because we might have 5 to 10 Gauss, which is a pretty strong magnetic field, whereas 0.0001 Tesla might not seem like a very strong field. So let's do an example of a problem. Say I have an old TV tube. I know we don't use these very much anymore, but it's called a cathode ray tube. And it literally was a vacuum tube that had a neck, had an electron gun that shoots an electron, and it would hit the phosphor on the screen and would create an image. Well, say I've got an electron in this TV tube, and it moves towards the front with a speed of 8 times 10 to the 6 meters per second, and it's in the x direction. Surrounding the neck are coils that produce a field of 0.025 Tesla that's directed at an angle 60 degrees to the x-axis, but it's in the xy plane. Find the force on the electron. Well, since both velocity and magnetic field are in the xy plane, we know that the force is going to be in the z direction. And then we can use our right-hand rule, look at V cross B, and we can see that it would normally point in the plus direction, but since we have a negative charge, we know it's going to be pointed down. So, We can see all this exactly if we just use our vector equation. The velocity, we said, is 8 times 10 to the 6 meters per second in the x direction. The magnetic field, we said, is 0.025, and it's points in the x and y direction. So we break the vector up into x and y components. So it's 0.025 cosine 60 in the x and 0.025 sine 60 in the y, and we calculate that out, and we get these values. So now we need to go V cross B. And we also know charge is minus E. It's just minus 1.6 times 10 to the minus 19 coulombs. So force is Q V cross B. So Q is minus E, V is in the x direction, and T is in the x and y direction. Now, we remember from cross product that x cross x is 0, and x cross y is z. So this term and this term we can neglect because x cross x is 0. So plug that together, we're going to get minus E times the velocity times the magnetic field in the x cross y direction. So it's minus 2.8 times 10 to the minus 14 newtons in the z direction. Now that was the force on a single charge. What if I have a lot of charges moving? In fact, what if I have a current in a conductor? What force exerts on that conductor due to the charge moving in it? So, when I have a current carrying wire and I put it in a magnetic field, that current, of course, is a collection of many charged particles in motion, and the direction of the force we can figure out is given by the right-hand rule. Now, we need some notation when we're looking at problems, because we are no longer just looking at in the x and y direction, but we need to consider the z direction, or in and out of the page. And in our book, dots represent an arrow coming at you. You kind of think of it, the way they modeled it is, if someone were to shoot an arrow at you, you'd see the point coming at you. Whereas if the magnetic field is going into the page, we're going to see a cross. That would be, say, the feathers on the end of the arrow going away from you. So in this case, I have a magnetic field in this region here, and I have a wire that there's no current in it, there's no force on it, it's just going to hang straight up and down. Now, as I create a magnetic field going up, and then B is into the page, so the velocity is up. I use my right hand rule, my finger is pointing up, I curl them down so that the magnetic field is going in, and my thumb is pointed off to the left, which shows that there is a force to the left on this wire. Now if I switch the direction of the current, and then I switch the direction of the force. Now I take my right hand rule, my finger is pointing down, they curl into the page, and now my thumb on my right hand is pointing to the right. So what's going on is there's a magnetic force on every single moving charge in the wire. And so the force is going to be Q times the drift velocity of the charge times crossed with the magnetic field. The total force is the product of the force on one charge times the total number of charges. So we have down here Q VD cross B is the force on one charge. N, little n, remember, is the charge densities, the charge per volume. And A is the cross-sectional area of the wire, and L is the length of the wire that we're considering. So NAL gives me the total number of charges in that little portion of the wire. So in terms of current, this becomes IL cross B, where L is a vector that points in the direction of the current and whose magnitude is the length of the segment. Then B is the magnetic field. What if I had some arbitrarily shaped wire, though? Let's look at a small wire segment. If I wanted to calculate the magnetic force on this whole wire, I would need to find the force on this little segment where ds is pointing in this direction, and the force would be I times the length, which in this case is ds cross B. In order to find the force on the entire wire then, I need to integrate over the wire. So it's a path integral. I integrate along the path of the wire. Well, let's look at several different cases. What if I have here this wire that's curved like this? L prime is going to be the vector sum of all these little ds's as we add them up. The magnetic force on the curved current-carrying wire in a uniform field is equal to that of a straight wire connecting the endpoints and carrying the same current. If I have a closed loop, though, let's say I have a wire that forms a closed loop, and I were to add up ds all the way around, the length elements form a closed loop, so the vector sum is 0, which means the net magnetic force acting on any closed current loop in a uniform magnetic field is 0. So let's look at a problem that deals with current in a conductor. Let's say I have this rod here that's allowed to roll on these two metal rails. The rod has a mass of 0.72 kilograms, a radius of 6 centimeters, and it rests on these rails that are 12 centimeters apart and that are 45 centimeters long. So I hook up a battery to these rails somehow, and I turn up the current, I turn up the voltage so I get a current of 45 amps going through this rod as shown. And let's say that rod can roll, and we're going to let it roll without slipping on the rails. I have a uniform magnetic field, 0.24 teslas, directed perpendicular to the rod and the rails, and pointing down as shown. So if it starts from rest, what is the speed of the rod as it leaves the rails? So first let's define some directions. Let's say x is going to the right, y is up, and z is coming straight out at us. So our current is going to be in the z direction. The magnetic field is going to be in the minus y direction. And the direction of motion of rolling is going to be in the x direction. So we know the force on this is I-L cross B. In this case, L is the length of the conductor, which is D. And the direction of L, we said it is the direction of the current, which would be in the z direction. We cross that with the magnetic field, which we said its field strength is B, and its direction is minus y. So z cross y is minus x, the minus goes away, and so the force is IdB, and the force is in the x direction. So we can then calculate the work done on the cylinder. Work is going to be integral of the force times the distance. In this case, force we know is IdB in the x direction, and ds is going to be in the direction that's going is dx in the x direction. So we plug that in, and x dot x equals 1, x hat dot x hat equals 1. And so we end up with the integral of IdB dx, and I'm going from 0 to the length of the rails. IdB is constant, it comes out, and I integrate along dx, and I'm just going to get L. Now, I know that the work done is equal to the change in kinetic energy. So our initial energy is 0, so it's just equal to the final kinetic energy. We have to figure out then what that energy is, because not only is the rod moving, but it's also rolling. So the kinetic energy is 1/2 mv squared plus 1/2 I omega squared. The moment of inertia of the cylinder here is that of a disk, 1/2 mr squared, and omega is v over r. I plug that in, and I get 1/2 times 1/2 is 1/4 plus 1/2. I'm going to get 3/4 mv squared. So now I can solve this for my velocity. Velocity is the square root of 4IL dB over 3 times the mass. And all those values are givens. We plug those in, and we get that the velocity of this cylinder as it leaves the rails is 1.07 meters per second. So let's review what we've talked about today. We introduced magnetic fields, talked a little bit about the history of them and what they look like for different north-south pole configurations. We said there's a force on charged particles that depends on the charge, the velocity, and the magnetic field. And lastly, we talked about the forces on current-carrying wires, forces I, L cross B, or if it's a arbitrarily curved wire, forces I times the integral of ds cross